All right, so let's start our class. Today, we are going to another topic, which is vector, scalar and vector quantity. Scalar and vector quantity. So the first thing is to define what a scalar is, and then examples of scalar, and then move on to vector. So a scalar is a quantity with magnitude but no direction. A quantity with magnitude but no direction, which implies that it has only number, size. The quantity can be described, or the physical property can be described by its size, its magnitude, but there is no direction. So example of scalar quantities are mass, temperature, energy, charge, are all examples of scalar quantity. So what is a vector quantity? A vector quantity is a quantity that has both magnitude and direction. Magnitude and direction, which means we can represent such quantities with magnitude, that is their size, and direction. Examples are velocity, force, momentum, electric field, acceleration. They are all examples of vectors. So symbolically, we can represent vector using a bold letter and arrow at the head. A bold letter and arrow head. So here we have a vector whose magnitude is the length, and then the direction is given to us here as the angle, the magnitude made with the horizontal line. So we can use the arrow as a vector. The head tells us of the direction of the vector. In real application, sometimes you would have come across, maybe when you are looking for a venue, you come across the name of the street somewhere on the road, and then you see arrow pointing to a particular direction. So that arrow gives you a clue of where the place you are looking for is. If you go all around Lagos Street, you will see notice of street and arrows. The arrow will guide you, will direct you to where you are going. So that is what the head of the arrow here indicates. The head indicates the direction. It points to where the quantity is heading to. So that is what we need to know about vector. Now, two vectors are said to be parallel vectors if they have same direction. So here we have two vectors, vector A and B. If you look at them, both of them are moving in the same direction. So this implies that they are parallel vectors. Vectors P and Q also are moving in the same direction, showing that they are parallel vectors. If the vectors are moving in opposite direction, they could be parallel, but of course, in opposite direction means that they are parallel but opposite direction. Now, two parallel vectors are said to be equal vectors if they have same magnitude. Now, before I move on parallel vectors. Now, when two vectors, I'll still say more on it when we get to addition of vectors. If these two vectors moving in the same direction could be added, but if the two vectors are moving in opposite direction, such as this, the magnitude of these two vectors will be subtraction. When they are in opposite direction, the magnitude is subtraction. When they are in the same direction, the magnitude is gotten by addition. When they are in the same direction, the magnitude is gotten by addition. When they are in opposite direction, the magnitude is gotten by subtraction. So two parallel vectors are said to be equal vectors if they have the same magnitude. So vector A is equal to vector B if they have the same magnitude. Vector P is equal to vector C if they have the same magnitude. And like I said before, when two vectors are moving in the same direction, their magnitude is gotten by addition. And if they are moving in opposite direction, their magnitude is gotten by subtraction. So look at this diagram here. For instance, vector A is moving this way. Vector A is moving in this direction. Vector B is moving in this direction. So now, if you look at the two vectors, the end of vector A is the beginning of vector B. Where vector A ends, it's where vector B begins. Remember tail and head. This is the tail region, and this is the head region. Head region for vector A. This is the tail region for vector B, and this is the head region for vector B. So when we have a situation like this where the head and the tail are together, we say that they are moving in the same direction, so we add them. So the case we have here, vector A moves down to this point, and then vector B takes from where vector A stopped. So it means that we are going to add them together. And then vector C is a magnitude. So putting them together, what I've explained so far, that gives us vector C is equal to vector A plus vector B. Another way to look at it is, if I'm moving round from starting from vector, the tail of vector A here, and then move round back to this point, I make a circle. So from my beginning to end will give me a zero. The sum will be a zero. But this zero is made up of vector A plus vector B, because they are moving in the same direction. Now, if you look at the arrowhead of vector C, it coincides with the arrowhead of vector B, which means that vector C is in a direction that is against vector B. So that is a minus. So we have B plus A plus B minus C is equal to 0. That the sum of the vectors, all the vectors A, B, C, the sum of vector A, B, C is equal to 0. But A is positive, B is positive, C is a negative vector. So A plus B minus C is equal to 0. Now, in that case, if I move minus C across the quality sign, that will give me C, vector C is equal to vector A plus vector B. So that brings us to this expression once again. So when two or more vectors are in the same direction, heading in the same direction, you add them. When they are heading in different direction, you subtract them. That is a rule that you should not forget in vector addition and subtraction. Now, rectangular components of two-dimension vectors. Rectangular component of two-dimension vectors. So here we have 2D vectors, vector A, that is two vectors, one along the y-axis, which is the vertical axis, and the other vector along the x-axis, which is the horizontal axis. So if I have a vector such as this, I can represent this vector AY and AX as expressed here. So the magnitude of my vector, which is the resultant here, is given as AXI plus AYJ. I and J are the unit vectors. They are the components of the unit vector AX and AY respectively. So the component of vector A along X, the unit component of vector A along the X-axis is I, while the unit component of vector A along the Y-axis is J. And for 3D, the unit component of A along the Z-axis is K. So we'll get to that point later. Now, we to find the angle, that is theta, which is considered as the direction, we can use any of the cosine, any of the trig function. We can use any of the trig function, which is sine theta is opposite over hypotenuse. Opposite over hypotenuse. The opposite is AY, while the hypotenuse is A. So AY over A is equal to sine theta, which implies that AY is equal to A sine theta, and that is a vertical component of that vector A. Then along the X-axis, we have AX. You are disturbing my class with plenty things that you are writing. So, adjacent over hypotenuse, this is the adjacent AX over hypotenuse, gives us cos theta. So, if we rearrange that expression, we'll have AX is equal to A cos theta. AX is equal to A cos theta. So AX is the horizontal component. Remember, we are looking at rectangular component of 2D vectors. So in rectangular components of 2D vector, that is 2 dimensions, we have X component and Y component. That is the vertical component and the horizontal component. The vertical component, which is this, and the horizontal component, which is AX is equal to A cos theta. So for instance, you could be given problems like, let's say the angle here is 30 degrees, and then here you have 5 meters. You are asked to find the vertical component and the horizontal component of this vector. The vertical component and the horizontal component of this vector. So the vertical component will be A subscript Y is equal to A sine theta. So if we substitute these values, the vertical component will be A subscript Y is equal to A, which is 5, sine theta, that is sine 30 degree. Sine 30 degree. Sine 30 degree. So sine 5 sine 30 degree will give us what? Do you have your calculator there with you?
Plus 5, sir.
Is that what? What's your
2.5, sir.
response? 2.5.
2.5, sir.
All right, so that gives us 2.5. So we have 2.5 meters. And then the x axis, that is horizontal component, will be 5. Ax will be equal to 5 cos 30 degree. So that will give us what?
4.3, sir.
4.3 meters.
Yes, sir.
4.3 meters. So now we have our vertical component and horizontal component. Sometimes you could be given the vertical and horizontal component and asked to write, find those of you writing, sending your names and details, you are disturbing me. It's popping up, popping up, popping up. So please stop for now. So if you are, assuming you are given values like 4, 4 meters and 3 meters. So, but please stop sending your names not for now. You are disturbing the class. Who is this? Jesse Ebuka. Stop sending your names for now. Nobody should type anything. Don't type anything. Don't chat. When you chat, it will be popping up and disturbing the class. Now you are given vertical component and horizontal component. You are asked to find the magnitude and the direction. So in this case, to find the magnitude, just see, when I said don't write anything, you are still writing, isn't it? So to find the magnitude, which is A is the magnitude, is given as square root ax square plus ay square. If you remember your elementary Pythagoras theorem. So use that Pythagoras theorem method to find your A. So this will be square root of 3 square plus 4 square. 3 square is 9 plus 16. 4 square is 16. So this gives us root 25. So square root of 25 is equal to 5. So our A is equal to 5 meters. Our A is equal to 5 meters. Now, to find this is the magnitude. Our A, which is the magnitude, is 5 meters. To find the direction, which is angle, theta, we can use the 3 functions to find the magnitude. So that will be theta. If we are using this, that will be theta. Theta is equal to sine inverse AY over A, which is sine inverse, which is second function. Sine inverse AY is 4, A is 5. So that is sine inverse of 0.8. We can also use cos theta, which is cos inverse AX over A. Or we can use theta equal to tan inverse AY over AX. But in all, since it has to do with AY and AX, it is preferred that you use theta is equal to tan inverse, that's the second function of tan, AY over AX, which is opposite over adjacent. So that would give you this angle. That will give you that angle. So that is how to find magnitude and direction. Magnitude and direction. So here you have the formula written down for you to find the magnitude for 2 dimensions. You will have A is equal to square root of A subscript X square plus AY square. And for the direction, theta is equal to tan inverse AY over AX. Now, for 3 dimensions, we add Z component. So if we add Z component to the 2 dimensions, we are going to add AX plus AY plus AZ. To find the magnitude of the 3D vectors is still the same Pythagoras theorem method. You find the square root of the squares of each of the components. Square root of the squares of each of the components. And then to find the direction. Now, this time, we cannot use, we cannot get the direction by applying just a single trig function, because Since it's a 3D, each of them makes angle with the magnitude. X is making an angle with the magnitude A. Y is making an angle with magnitude A. Z is making an angle with magnitude A. So the angle between AX and magnitude A is alpha. The angle between AY and magnitude A is beta. And the angle between AZ and magnitude A is gamma. So when you are asked to find the direction, they are indirectly asking you to find the direction cosine. Direction cosine. And by that, we make use of this formula. So we are going to find all the angles, alpha, beta, and gamma. You are not finding only one angle. Unlike two dimensions, where when you are asked to find the direction, you are to find just one angle here. But for 3D, you are going to find each angle the component vector makes with the magnitude or resultant vector. So this is the formula for that.
Yes.
Now, addition of vectors. Addition of vectors. When you are given two or more vectors, you add them by components. When you are given two vectors or more vectors, add them by components. So when you are given two or more vectors to add, you add them, you do so by adding them by component. So here we have vector A in 3 dimensions and vector B in 3 dimensions. And we are asked to add A and B to form a single resultant vector. So to do so, we are going to add the components together. So that will be components for A along the x-axis is I. Component for B along the x-axis is I. So we add these two together. We add for Y, we add them together. Then we add Z together for both vectors. So that is how to add. So AX plus BX will give us the resultant vector X component. AY plus BY will give us the resultant vector Y component. And AZ plus BZ will give us resultant Z component. That is for addition. We can also subtract. Even when you are subtracting, you subtract by according to components. Now, multiplication of vector. Multiplication of vectors. So there are 2 ways to carry out vector multiplication. The first is by scalar. scalar method. In this type of multiplication, we multiply a vector by just a number. Remember that scalar is just a number. When you hear the word scalar, it's just a specific number. So by applying multiplication method using scalar, multiplying vector by a scalar, we multiply the vector by a number that is given. For instance, you could be given a vector A, and then you are asked to find 2A, or you are asked to find 3A, or 4A, and so on. So here, 2 is the scalar, and A is the vector. Here, 3 is the scalar, and A is a vector. Here, 4 is the scalar, and A is a vector. So what this implies is you multiply the vector by 2 across. Multiply the vector across by 2. For instance, if we are given a vector A is equal to, let's say, 2D vector, 2I plus 3J, and you are asked to find 2A. So that will be 4I plus 6J. If you are asked to find 3A, that will be 3 times 2 is 6I plus 3 times 3 is 9J. If you are asked to find 4A, 4 times 2 is 8I. 4 times 3 is 12J. So that is how multiplying a vector by scalar is carried out. That is one type of multiplication of vector. Now, the second type of multiplication of vector is by multiplying a vector with another vector. Is by multiplying a vector with another vector. In this case, we can also apply, we have 2 ways in which a vector can multiply another vector. We have 2 ways in which a vector can multiply another vector. The first one is called the dot or scalar product.
Sir, we can't hear you. You're muted.
All right. So I was saying that there are 2 ways to multiply a vector by a vector. The first way is by dot product method or scalar product method. So, and that is given as A dot B. For instance, if you are given 2 vectors, we have A dot B is equal to AB cos theta. A dot B are the 2 vectors given. A dot B are the 2 vectors given. They could be 3D vectors or 2D vectors. While the A here is the magnitude of vector A. A is magnitude of vector the A here, the A here, or A and B here, are the magnitude of vector A and B here respectively. So that is the first way. The second way of multiplying vector by vector is known as the vector product or cross product. Vector product or cross product. So in this case, we have A cross B is equal to AB sine theta. Now, you notice that there is a unit vector here. So this tells us that your final answer, when you use this method, will give you a vector, will come in a vector form. While here, your final answer will come in a scalar form, just a number, a scalar form. That is why this first one is also called a scalar product, while the second method is called a vector product. So note the difference between dot product and cross product. Dot product will produce a scalar at the end of the multiplication, while cross product will produce a vector at the end of the multiplication exercise. So when we start solving examples, you will understand it better. Now, also note that the scalar product of two same unit vector is 1, and two different unit vector is 2. Is 0, which implies that when you are applying a scalar product method or dot product method to multiply two vectors, you can only multiply by their component. So you consider same components, similar components. Just like during addition, we added AX plus BX. Similarly here, if we want to multiply, applying scalar product method, it will be by components. It will be by component, and that is I dot I, J dot J, and K dot K. That will give you 1. But if you cross multiply I dot J, J dot K, and K dot I will give you 0. That is for scalar. But for cross product, like the name implies, cross product will be I and J will go, J and K will go, and K and I will give you 1. In cross product, the process of applying this is for cross product and dot product are like opposite, because cross product has to do with cos theta, while cross product has to do with sin theta, while dot product has to do with cos theta. Now, one other way I want to explain it to you is that, look, for instance, I have this. diagram. This is X and this is Y. X and Y are perpendicular. The angle between them is 90 degrees. So now, if I 90 degrees, so sine 90 degree will give you 1, but cos 90 degree will give you 0. Cos 90 degree will give you 0, sine 90 degree will give you 1. Now, which means that if I multiply Y and X, if I multiply Y and X together, the angle between them is 90. The angle between them is 90. In our formula, we had A dot B cos theta. So if I multiply I and J, the angle between them is 90. Cos 90 will give me 0. But in the other formula where we have AB sine theta, if I multiply Y and X, the angle between them is 90. Sine 90 is equal to 1. Sine 90 is equal to 1. Now, coming to I dot I. I dot I simply means that the two vectors are parallel. I dot I. The two vectors are in the same direction. So if the two vectors are in the same direction, they are parallel, the angle between them will be 0. The angle between them will be 0. So cos 0, if I multiply I dot I, the angle between them is 0. Cos 0 is equal to 1. But if I multiply I dot I, here in the second case, the angle between them is 0. Sine 0 is equal to 0. So the two formulas are opposite to one another. What applies in the other one does not apply in the other one. So note this concept or condition for both of them. So I want to believe by the time we start solving examples, you will understand better. So let's look at another thing you need to know is for cross product, when I multiply I and J will give me a K. When I multiply J and K, it will give me a I. And when I multiply K and I, it will give me a J. Because alphabetically we have I, J, K. So I before J before K, it goes in that circle. So if I put I before J, I'll get a positive K. But if I put J here, if I put J before I, alphabetically is in the other, in the reverse. So that will give me a negative K. J comes before K. If I multiply J and K, it will give me a positive I. But if I put K before J and multiply, it will give me a negative I. Then when I get to K in the circle, I move back to I again. I, J, K, I, J, K, I, J. That is the way it goes in that circle. So K times I gives me a J. If I put I times K, it will give me a minus J. So note this movement as well. So the setup for vector product is this. We use the matrix method. So this is how it goes. We have I, J, K. This is a positive. I is positive, J is negative, K is positive. So remember this explanation here. So if I want to find vector I, it means that I must multiply J and K to get vector I. So in that case, I will consider multiplying this. So when I multiply this, I will get I. So when I multiply this, I will get I. So now, AY, BZ minus AZ, BY will give me AI. So that is what you have here. AY, BZ minus, remember AY is J, multiplying BZ, which is a K. That will give me a I. Then BY, and BY is a J, multiplying KZ, that will give me also what? An I. So we have AY, BZ minus AZ, BY. So this is a plus. Then when we come to J, we want to look for J. So in this case, we are going to multiply to get a J, it will be K and I. So we multiply K, vector K and I. Multiply vector K and I will give us J. So that is AX BZ, AX BZ minus AZ BX gives us a J. And then to find our K, if we want to find K, it means that we multiply I and J. So we choose these two vectors. So if we multiply AX BY minus BX AY, that gives us a K. So by the time we apply numerical examples, you will understand better. So let's look at this example. Find the dot product of U given as -4, 5 minus 1, and V 3 minus 3, 1. So now this tells us that U and V are three-dimensional vectors. We are asked to determine if U and V are orthogonal. Orthogonal means that is they are perpendicular, which is the angle between them is 90 degrees. So how do we do that? Our U is given vector U is given as minus 4I plus 5J minus K. According to the question, -4, 5 and minus 1. So that is minus 4i plus 5j minus k. So what will be the magnitude of u? Magnitude of u is equal to square root 4 square plus 5 square plus 1 square. Now, you notice that I removed the minus because in the minus will not count because you are already squaring. Minus 4 square the square will cancel the minus. Here also the square will cancel the minus. So it will not affect our answer. So this will be 4 square is 16, 5 square is 25, and plus
Sorry, I'm muted.
Sorry, I'm muted.
square root uh, e e plus e equal to minus 3j k. So the magnitude of vector equal to square root 3 square plus 3 square. That gives us square root of 3 times 3 square is 9. 9 plus 9 again, that is 18 plus 1, 19. So we have 19 for U and for U is equal to square root of 18. Now, we have to find the dot product. which is u theta is not given to us. So what we should do is minus 4 5 to multiply complement. This will give us minus 12 5 will give us minus 12 minus 15 minus 1 will give us minus 28. That is u is 28. So how do we know if it's orthogonal? So we are done, we find the dot product. This is minus 28. We got that right. How do we know if it's orthogonal? And from this formula, we make cos theta the subject. So that will be minus 28 is square root of what is square root of 19? Square root of 19. So if you simplify this, then find the second function. So theta becomes cos, that's the second function of cos theta. Simplify this. Now, by the time you substitute this, you discover that the answer is not 90. Theta is not 90. Since theta is not 90, it means that it is not orthogonal. Vector D and E are not orthogonal. If they are 90, if it is 90, if the angle is 90, then vector U and V will be said to be orthogonal. So is that clear to everyone? So we are going to end the class here because this class is 1 hour. Okay, solve more examples. Except that the class is done. I'll send the YouTube link to your class rep before you to the platform so that you can go back and